Welcome back to the deep dive. We're here again, taking a stack of fascinating sources and, well, pulling out the essential insights just for you. Today, we're jumping into a world that's this really unique mix of visual art, pure logic, and actually some surprisingly deep computational ideas. We're talking about nonograms, those grid puzzles, where you fill in squares and bit by bit, a hidden picture starts to appear. Now, you might know them by other names too: Picross, Hanji, maybe paint by numbers, or gridlers. Even pick-a-pick shows how far they've spread, right? The core idea is, well, pretty clever. Numbers along the edges of the grid. They tell you exactly how many squares to color in for each row and column, and boom, you get an image. So our mission today is to unpack the history, which is more surprising than you might think. Dig into the techniques people use to actually solve them, and look at how they went from paper puzzles to all over our screens.
And it really is a fantastic subject for this deep dive. It hits that sweet spot for intellectual curiosity, doesn't it? It's not just about coloring squares randomly. It's pure deductive reasoning. You're training your brain, making connections, ruling things out, almost like a detective. And that moment, that aha, when the numbers finally click into a recognizable picture, that really shows the satisfaction of focused logical thinking. It's great mental exercise.
That's a perfect way to put it. Those aha moments are definitely rewarding. So, okay, these puzzles feel kind of timeless almost. Simple grids, simple rules. Where did they actually come from? Have they been around forever? Or...
That's one of the most interesting parts. They haven't been around forever at all. And the origin story is, well, it's a dual invention. Happened independently in Japan, both back in 1987, which is pretty remarkable.
Wow, two people at the same time.
Exactly. The first was Ishida. She was a graphics editor, and she came up with her version. She called them window art puzzles after she won this competition. The competition involved creating images by, get this, turning skyscraper lights on and off, like a giant real-world pixel grid.
No way! That's brilliant.
Isn't it? And then, completely separately, a puzzle writer named Tetsuya Nishio published very similar puzzles in a magazine. No known connection between them. It's quite rare, that kind of parallel invention. Suggests the idea itself had a sort of inherent appeal just waiting to be discovered.
Okay, so two inventors, Japan, 1987. How did they go from that, relatively local start to becoming this global puzzle phenomenon?
Well, a lot of that credit goes to a British puzzle collector named James Deldity. He stumbled upon Ishida's window art puzzles, and he's the one who actually coined the name nonogram. It's a mix of nonogram from Ishida's name and, well, diagram. Pretty clever.
Nonogram. Okay, that makes sense.
He saw the potential, and he managed to get them published weekly in the Telegraph newspaper in the UK, starting back in 1990. That was really the breakthrough moment for global popularity. And what's fascinating is this sort of boomerang effect. They got so popular worldwide that their success actually led to them being re-imported into Japan. They became huge in major Japanese newspapers, but only after they'd made it big internationally. Quite a journey.
That is a strange path. So let's get down to brass tacks. You've got a puzzle in front of you. What's the absolute basic rule? How do you start?
Right. The fundamental principle is actually quite straightforward. The numbers outside the grid, they tell you the lengths of consecutive blocks of filled-in cells. It's usually black, but let's stick with that for now. And this is critical. There must be at least one blank square separating consecutive blocks in the same line.
Okay, so if a row says 4, 8, 3.
Exactly. That means you'll have a block of 4 black cells, then at least one blank, then a block of 8 black cells, another blank or more, and then finally a block of 3 black cells. The order matters.
Got it. The space is key. But I've definitely seen color nonograms. They always look way harder. How do they work?
They definitely add a layer of complexity, yes.
Yeah.
In color puzzles, the clue numbers themselves are colored. Pink 3, blue 2, whatever it might be. And here's the big difference. If you have 2 blocks of different colors next to each other, according to the clues, they might not have a space between them. The color change itself acts as the separation. So red 4 followed by a blue 3 could be 4 red cells immediately touching 3 blue cells. This lack of a guaranteed space between different colors often makes them trickier, especially, if the puzzle uses similar shades or just a few distinct colors. Less information to work with.
Wow. Yeah, that sounds like it really ramps up the difficulty. So whether it's black and white or color, what's the one rule you absolutely cannot break?
The golden rule, the absolute bedrock of solving nonograms. Never. Guess. Never. Every single square you fill in or mark as empty must be based on 100% logical deduction from the clues you have. And just as important is marking the cells must be empty. People often use dots or X's. Why? Because eliminating possibilities is just as crucial as confirming filled cells. It narrows your focus. Guessing just leads to chaos.
Right, avoid the chaos. You also mentioned working on rows and columns together. Why is that so important? Can't I just, solve one row completely, then move on?
You could try, but you'd get stuck very, very quickly on anything but the simplest puzzles. Think of it like a conversation. The information you deduce in a row, maybe, you figure out where a small block can't go, often gives you the exact clue you need to place something in a column, and vice versa. It's this constant back and forth, this cross-referencing between the horizontal and vertical clues that lets you chip away at the puzzle and make progress. It's essential.
Okay. Cross-referencing is king.
Hmm.
Let's get into some of those techniques then. People usually start with more basic stuff, right? Just looking at one line at a time.
Exactly. Those are the foundations. The most obvious is complete lines. If a row clue is 0, well, the whole row is empty. Mark it all with X's. Or if it's a 10 by 10 grid and the clue is 10, then the whole row is filled. Easy start.
Makes sense. What's next?
One of the most powerful early techniques is called overlap. It sounds simple, but it's incredibly useful. You basically look at a single clue, say 8 in a 10-cell row. You mentally slide that block of 8 all the way to the left. Then you slide it all the way to the right. The squares that are covered in both of those extreme positions, they have to be filled in. In that 8 in a 10 wide row example, the middle 6 squares must be black, no matter what.
Ah, I see. Because they overlap in every possible placement. That's clever.
It is, and related to that is the idea of simple spaces, or marking cells out of range.
How does that work?
You figure out the maximum reach of the blocks. If a cell is so far to one end that no possible placement of any block in that line could ever reach it, then you know that cell must be empty. Mark it with an X.
Okay, eliminating possibilities again.
Precisely. And there are other handy single-line tricks, too. Things like forcing, where maybe an empty space you've marked forces a block next to it into a specific position. Or glue. Sometimes finding just one filled cell right near the edge of the grid can suddenly fix a whole block against that edge. It glues it in place.
And you mentioned punctuating.
Yes. Very important habit. Once you've definitively placed a block and the spaces required next to it, mark those spaces immediately. It confirms that part is done and prevents you from accidentally extending the block later, like putting a period on a sentence.
These single-line tricks sound powerful, but I know some puzzles just stop yielding to those. You get stuck. What happens then?
That's when you need to step up to the more advanced multi-line techniques. This is where the real, beautiful, complex logic comes in sometimes.
Okay, I'm ready. What's first?
One technique, which some purists debate but is logically sound if the puzzle conditions are right, is symmetry. If you know a puzzle has a unique solution and its grid or clues are symmetrical, then the final picture must also be symmetrical.
So you can sort of mirror deductions across the center line?
Potentially, yes. It can give you hints, especially about cells along the axis of symmetry. It's a powerful shortcut if applicable.
Interesting. What about edge logic? That sounds like it involves more than one line.
It absolutely does. Edge logic, or sometimes boundary logic, is often used near the edges, as the name suggests. You basically look at, say, a row near the top edge. You might have a hypothetical placement for the first block in that row. Then you check, does this placement create a contradiction or an impossible situation in the column? It intersects.
Ah, like an if-then test.
Exactly. If placing block A here means column B becomes unsolvable, then block A cannot go there. You rule out possibilities by checking their consequences in adjacent lines. It's very satisfying when it works.
Okay, cool. Then there's two-way logic. Sounds like exploring options.
It is in a controlled way.
Yeah.
You find a situation where, based on your deduction so far, a certain block can only possibly fit in one of two specific locations. You then mentally check both scenarios. If a particular cell is, say, black in scenario 1, and it's also black in scenario 2, then you know it must be black in the real solution, regardless of which scenario turns out to be correct.
So you find the common certainties between the only two possibilities.
Precisely. It lets you make progress even when you can't yet decide between the two options definitively.
And I've also heard people mention things like smile logic and summing. They sound a bit more obscure.
They can be. Smile logic often refers to patterns, sometimes involving lots of one clues in adjacent columns, that can force an alternating checkerboard-like pattern in a region. And summing is more mathematical. You might look at a small region of the grid, add up the total number of black cells required by the row clues in that region, and compare it to the total required by the column clues in the same region. Sometimes discrepancies reveal forced empty or filled cells. Quite advanced stuff.
Definitely sounds like it requires some serious brain power. It's amazing how these evolved from simple paper grids. How did they make that leap to, computers and phones?
That's a really important part of their story. Nintendo played a huge role here. They trademarked the name Picross, which is just short for picture crossword.
Ah, Picross. I definitely know that name.
Right, and they brought it to a massive audience with
Yeah.
games like Mario's Picross for the original Game Boy back in 1995. What's key is that Mario's Picross was one of the few early nonogram games actually released outside Japan. That really kicked off the digital craze globally.
So Nintendo was the pioneer there.
A major one, yes. And a company called Jupiter Corporation has been incredibly prolific since then. They've made tons of Picross games for Nintendo's handhelds, the DS, the 3DS, and now loads for the Switch. They've really kept that digital flame alive.
And now, of course, you can find them everywhere. Mobile apps, websites. It's so easy to just pull one up and play.
Absolutely, that accessibility is huge. And the digital versions often add helpful features like hint systems or automatically checking for errors, which can be nice for learners or if you just get really stuck.
Yeah, those error checks save a lot of frustration sometimes.
But this brings up an interesting technical point. How do computers actually solve these things or provide hints? For computer scientists, solving nonograms in general is what's called an NP-complete problem.
NP-complete, what does that mean in plain English?
It basically means it's computationally very hard for a computer to guarantee finding a solution for any possible nonogram quickly. Well, it's extremely difficult, likely impossible in what they call polynomial time, unless a major mathematical breakthrough happens, BNP.
So even computers find them tough.
In the general case, yes. It speaks to the inherent logical depth. But that doesn't mean computers can't solve them. Efficient software solvers exist. They often use clever algorithms, like backtracking. This means they systematically explore possibilities, but crucially, they prune branches of the search that lead to contradictions. It avoids checking every single combination.
Okay, so they're smart about searching. That makes sense. It also makes me feel better about finding them difficult myself sometimes.
Exactly. It puts our human aha moments into perspective.
So, difficulty. It's not just about making the grid bigger, is it? What actually makes one nonogram harder than another?
That's a great question. And no, it's definitely not just size. You could have a huge 50 by 50 grid that's actually quite easy if the picture's simple, maybe big blocks, lots of empty space. Conversely, a small 15 by 15 puzzle could be incredibly difficult if it's highly detailed, with lots of small gaps and intricate patterns.
So detail matters more than size.
Often, yes. And the density of filled squares plays a role too. Puzzles that are mostly empty or mostly full tend to be easier because the constraints are tighter. It's often that middle ground density that creates the most ambiguity and challenge.
And what about the clue numbers themselves?
Huge impact. Generally, large numbers, long runs of squares make things easier. A clue like 12 in a 15-wide row gives you a lot of immediate overlap information. But lots of small numbers, especially many ones, that can make a puzzle much harder. There's less initial information, fewer obvious starting points, and you often rely more on those advanced multi-line techniques.
Right, those dreaded rows of ones.
We can even get a bit more technical. We talk about simple nonograms. Those you can solve using only those single-line logic steps we discussed, like overlap and simple spaces. Computers use operations like settle for these. Then you have non-simple nonograms. These require looking at multiple lines at once to make progress. Maybe using techniques like considering 4 cells at the intersection of 2 rows and 2 columns simultaneously, something solvers might call a 2-on-2 solver or 4 solver. That's a definite step up in logical complexity.
So you have to look at interactions between lines.
You absolutely do. And for the really tough ones, you might even need look-ahead strategies.
Look ahead, like planning moves in chess.
Kind of, yeah. You mentally test a hypothesis, what if this square is black? And trace the logical consequences a few steps down the line across multiple rows and columns to see if it leads to a contradiction before you actually commit to marking the square. And one final thorny issue. Sometimes puzzles can have switching components.
Switching components.
Imagine a small 2x2 area or a more complex region where you could swap the black and white cells entirely, and the row and column clues for that specific region would still be satisfied.
So, multiple correct solutions.
Exactly. Or at least multiple possibilities for a section that pure logic, based only on the clues, cannot resolve. This makes solving uniquely incredibly difficult, sometimes impossible without an extra hint or rule. True uniqueness is usually a goal of puzzle creators, though.
Wow. Okay, we've covered a lot of ground here. We've gone from these unexpected origins in Japan, skyscraper lights and all, through the core rules, the basic and advanced logic. right up to NP completeness in the digital age. It really is this fascinating intersection of art, logic, and computation.
It truly is. And if you step back, it's quite remarkable, isn't it? How a very simple set of rules numbers telling you about blocks and spaces can generate this enormous spectrum of complexity. From puzzles you can solve in a coffee break to problems that challenge computer science. It really highlights the depth that can be hidden in seemingly simple entertainment and how much our brains enjoy that process of discovery and deduction.
Absolutely. So whether you've always called them nonograms or Picross or Hanji, or maybe you're just hearing about them now, hopefully you have a new appreciation for what's going on behind the scenes. You've got the history, the techniques, you're ready to tackle them with fresh eyes. So here's your final thought to ponder. Armed with all this insight into the logic, the history, the art, what hidden picture will you set out to uncover next?